Let's analyze the solubility of ethanol in water. Figure it out. Remember, we need to, if we have just pure ethanol, we will have intermolecular forces between these molecules of the same kind. And here we have London dispersion forces. We also have dipole-dipole. But the strongest is hydrogen bonding, which is, say I have one molecule of ethanol here, and I will have another. Remember that you identify if the molecule can form hydrogen bonding when you have a hydrogen attached to either oxygen or nitrogen. And so that's another molecule of ethanol, and you can have like a network like this. And many more. That is, those are the interactions that I would need to be breaking if I want to dissolve ethanol in water. So the process, remember, that is governed by the changes here. So delta G of solvation, it will have changes in enthalpy, and we will have changes in entropy. Same of solvation. What's happening here? So if I want to dissolve this and that, I will need to break these interactions. That goes into this term. So now breaking those. This contribution, I'll say breaking, this is delta H. So bond breaking, even though, or breaking those intermolecular forces. Let's say the solute, which I'm going to say that solute is always the one that is in lesser amount. So we're going to say that we have less ethanol than water. But just to define solute, so I need to break those interactions. That's going to cost me some energy, and I have an important interaction here. Then I need to, as for the enthalpy term, I need to break interactions of the solvent. And water also has the most important interaction being hydrogen bonding. We don't even have that van der Waals, so we're going to have a network. Right, so I need to break those. That's energy that I need to put in. So this is positive, and this is positive. So solvent. And I'm going to have another change in enthalpy, which is the enthalpy of the mix. And when you're mixing these two, you're looking at, for the process to be product favor or spontaneous, you want to form new interactions that actually compensate for the loss of those. And in fact, it does. When you have ethanol in water, you can replace those hydrogen bond forces by new ones. So new interactions between ethanol and water will compensate for this one that I need to break and that I need to break. So overall, this is negative. Remember that when bonds form, energy is released. To break those interactions, you need to supply energy. But this term, largely, this is compensating for this, for the energy. So that is in regard to the enthalpy term. I know it's favorable because, again, the nature of this interaction is the same as here. And the two molecules have, say, relatively low molar mass. Okay, so now let's look at the entropy. When we look at the entropy term, so this two, let's say we break even about the same. But always when you mix, you increase the degree of freedom, the level of state disorder. So you will have here in the delta S of solvation, you will have that change in what is in the solute. It was organized. I'm breaking those apart. And there's a change in entropy in the solvent. This organization is going to be changed. And we have an entropy of the mix. We know this, when this is large, like in the case of salts, being separated in ions and being dispersed with a solvent, this term is very large. And that, say, governs that in many cases. So in this here, we will have that the enthalpy term is compensating the new interactions that form compensate for the ones that I need to break in terms of same strength of intermolecular forces, So strongest here being hydrogen bonding, same here. And I'm forming new hydrogen bonds to compensate for that. So at least is overall compensated, but now I have the entropy of the mix. I'm going to have those molecules mixed together. So it works in, so methanol, ethanol up to, I have let's see, the solubility data of the alcohols in the series. I have that. Well, can't find it. All right, so but anyways, what we have in the series is that methanol is pretty much freely soluble in all proportions with water. Ethanol is also very soluble. Propanol now have 3 carbon also. But when I go to butanol, 1, 2, 3, 4, now the solubility starts to decrease. So we notice that what happened now in this series. Now we are increasing the carbon change. And what we want to be looking at is that we want a portion of, we have a portion of the molecule that is mostly same size. This we're going to say is hydrophilic, meaning philia is I like. So hydrophilic versus hydrophobic, where the carbons are. Hydrophobic. So we have, say, 2 parts in the molecule. I increase the number of carbons. The hydrophobic portion is now larger. And now it cannot start playing more a role into the solution. So overall, this molecule now starts to be less soluble than the previous. So freely soluble, pretty much miscible in all proportions. But now it's not the case for butanol, in even less soluble as we go pentanol, hexanol, etc. 1, 2, 3, 4, 5, and so on. Because now the nonpolar part weighs more. So understanding that in terms of intermolecular forces, we still have the hydrogen bonding. But I also have increasing, as this increases in size, more important here, the London dispersion forces. And as this is in water, we don't have as, not as, to the compensation here to the same degree. I cannot form as many interactions of hydrogen bonding having this long chain. And these are weaker forces. If I don't have that compensation here in the, when we mix, again, because I have all this part being hydrophobic, if I don't have that compensation to make up for the being about the same that we have in water, for example, if that does not compensate, then it's not likely to dissolve as well. So this is what we call the hydrophobic effect, when we don't have that compensation of having the same number of interactions of the same type. So here we will have more, say this mix is smaller, but now I have a long chain and not as many chances of form hydrogen bonding. In terms of entropy, it also, there is a discussion, say, about entropy. Liquid water is very organized. As I introduce molecules like more lipophilic, then the bigger it becomes. Water's, in regards to the enthalpy and entropy term, water wants to still have those hydrogen bonds because this is stabilizing. So they tend to organize, and let's say, in a way so that they can preserve those interactions. So now, if I have molecules with a large, say, large hydrophobic part in small hydrophobic, and I have all of that. Water tends to organize and keep this together. And these molecules also, only being able to interact with water like that, they cannot provide that kind of a network. So into, say, extreme level, we can see the formation of something that we call micelles. And these are long carbon chains. So when we have molecules with a large hydrophobic portion, such as this, but in the case of, this is even more, to illustrate the point, this is how soaps and detergent works. So this is a salt of a carboxylic acid. They are long side chains. They tend to organize in structures like a sphere called micelles. Micelles. In that micelle, the hydrophobic portion will be all together in the hydrophilic is here in the outside. And water organizes around that, say, like here. H, O, H, and so on. So now we will have two phases, essentially. But when we have a liquid such as that, we will see drops of the alcohol no longer being dissolved. When we have this species, now when we have micelles, we will have, say, like a bubble, a sphere, and this has special properties. This is used in soaps and detergents because grime, oil, and stuff like that in our dirty clothes, for example, can be trapped in here. I'm going to say oily things can be trapped inside the micelle because they will be similar in polarity, so low polarity, hydrophobic with hydrophobic. But they are dispersed, these little particles, the micelles, within the water due to these interactions. So that's how soaps and detergents clean. But overall, what we have then, hydrophobic effect, when the hydrophobic portion of the molecules is now having more weight relative to the hydrophilic part, we will have separation of layers. We will have one, say, organic layer that's mostly formed by this, and the other, when we're doing, you will see that at the lab when doing extractions. You will see a clear limit between two phases because there are substances that will not dissolve in water. These are called immiscible. So we will have a lot of applications of that.